Hello, welcome to a video discussing section 3.3 on differentiation rules. So here we're going to talk about some shortcuts you can use to take the derivative of a function, and I will cover up to the middle of page 3. So we're starting on page 1 here. So if I read the little blurb here, first let's do these problems using our basic definition of the derivative of function f with respect to x, which is hopefully now firmly engraved in our hearts. And of course, we had a quiz on this too. So f prime of x equals the following. The limit as h approaches 0 of f of x plus h minus f of x over h. So let's use that rule for problem number 1. So your function is 7. I take the limit as h approaches 0 of f of x plus h minus f of x over h. Well, what is f of x plus h? Well, if I replace this with x plus h, the outcome is still 7, of course. f of x is also 7. And we can't get lazy. You do have to plug in the limit notation here. You're taking the limit as h approaches 0 of 0 over h. Now, yes, h is approaching 0, but h is not exactly 0. And 0 divided by any number, or any non-zero number, remember, h is approaching 0, so h is not exactly 0. That's always going to equal 0. So this limit is just 0. So what this tells us is that when you take the derivative of a constant function, so f of x equals c, where c is a constant, then your derivative is just going to be 0. And graphically it makes sense, because if I graph y equals 7, the slope is 0. And we know the slope of the tangent line to a curve is the derivative. Of course, if I drew a tangent line to a horizontal line, it's going to coincide, and the slope of that red line is 0, if that red line is the derivative of f of x equals 7. Now let's look at another one. Let's look at problem 2. f of x equals x, find f prime of x. Well, I'll do this again. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So if I replace x with x plus h, then this becomes x plus h, of course. So limit as h approaches 0 of x plus h. Fx, of course, is x straight up, 5 of h. Those cancel. H over h, of course, is 1. And we've talked about limits of constants are the value of the constant themselves. You just get 1. Let's try this again. But here, actually, we don't need to go through the limit definition. We already know from section 3.1 that f prime of x here is going to equal 2x. Here, we already know this also, 3x squared. Here, we can kind of gather, I mean, we'll work this out, but hopefully if we're finding a trend here, I'm probably going to expect this to be 4x cubed. Notice how x squared was 2x, x cubed was 3x squared. So if we look for patterns, probably this will be 4x cubed. Let's go ahead and prove it really quickly. Now remember, if you do raise them to the 4 power, like a binomial, you wind up getting this. That's using the binomial theorem, which hopefully you guys covered in pre-calculus. But if you need a little help with that, just ask and I can help you out. And the coefficients, by the way, come from Pascal's triangle, which follows this pattern where you put 1, 2 1s, and then you add these two numbers here to get 2, put 1s on the side, add these two numbers, get 3s. And those will represent the coefficients from that binomial expansion. So again, if I take the derivative of this, the limit as h approaches 0 of f of x plus h minus f of x over h. So again, replace this with x plus h. I have x plus h to the 4 power, which we'll have to expand that, and fx, of course, is x4. H, limit as h approaches 0. If I expand this, this will be fun. I'm just kidding. Actually, it's not too bad because I have the formula, so I can just use it. Oh, yikes. Okay, this is good for the Google form. I made my official mistake for today. That's supposed to, I had that incorrect. That's supposed to be 14641 for the expansion. My apologies. So hopefully you're scratching your head about a few minutes ago. Like, what's Mr. Reed doing here? I caught myself because I knew I had another term here. And of course, things wouldn't cancel out quite as nicely, and I would discover that hopefully. Or I would not get 4x cubed, which I expect to be the answer. Now things should cross off very, very nicely. X4s go away. And I can factor out h from the top. 4x cubed plus 6x squared h plus 4x h squared plus h cubed all over h. And then plug in 0 for h, and you get 4x cubed. And the rest just kind of all just go away. And you get 4x cubed. So again, we're noticing this pattern here, that we have a power function, x raised to some power, and it seems as though the derivative is a degree less than the original function, and that the exponent previously now becomes a new coefficient. So this leads us to a very important rule that we're going to talk about that will be a lifesaver. If f of x equals x to the n power, then your derivative is just going to be n times x to the n minus 1 power. Or sometimes we'd like to write like this as a derivative operator. That's a derivative operator. So you're taking the derivative of x to the n. This is another way of writing it. That's all. Different notation. That's all. So for example, x to the 8th, I know is 8 times x to the 7th power. Or what if f of x equals x to the 100th power? Now I know the derivative is going to be 100 times x to the 99th power. For problem 7, fx equals 11x to the 4, find f prime of x using the definition of f prime of x as a limit. Excuse me. So in this case, I'm going to take, that's going to equal the limit as h approaches 0 of f of x plus h minus f of x all over h. And of course, if I plug that in, I get all this work here. And I could probably break this off like that. And notice I factor in 11 from here and here. I can take the limits of those separately. And that's just going to be 11, limit of any constant still is constant, times, and this right here, we already know from our previous example, it's just the derivative of x to the 4 power, which I know is 4x cubed. I get 44x cubed. So what this tells me is that if I have a constant being multiplied to a power function, my derivative is just going to be that constant times the derivative of that power function. So it's called the constant multiple rule. the derivative will be just c times derivative of u with respect to x. So in this case, that's 1/5 times the derivative of x to the 7. And sometimes I'll just do this little accent mark to show I'm taking the derivative of it. Or you can write like this, 1/5 times d dx of x7. And if I work that out, I get 1/5 7 to the x to the 6th power, or 7/5 times x to the 6th power. So u, just so you know, for rule number 3 here, u is just a function in terms of x. So in this case, that could be like 30 u of x. So sometimes we use u as a notation here. We got some more examples to talk about, and we're going to end by after problem number 11.